Okay, so the next topic we're going to go over is something called Avogadro's number, which is often referred to as the mole. I wanted to briefly introduce how this number was derived though, and it's kind of interesting. So let's take this example. So let's take magnesium. And if you look at the periodic table, the symbol for magnesium is capital M, lowercase g, and it has an atomic weight. Again, you can find this on the periodic table. It's going to be the average of all the natural isotopes, but it's going to have an average atomic weight of 24.31 atomic mass units, which has that little U symbol. All right. I also told you that we have these really fancy instruments known as mass spectrometers that can find the exact mass for an individual atom even, which is kind of cool. So in this case, we can find the average mass. So the average magnesium atom has a mass of, let's see, it's 4.037 times 10 to the negative 23rd grams. Sorry, that's not the greatest 3, but you get the idea. It's a really, really, really tiny mass. So here's the interesting thing, is you can do this thought experiment where you could say, what number of magnesium atoms would equal the atomic weight of magnesium if it were measured in grams. Not AMU. Okay, so this was the thought experiment that I was thinking of, and let's try to work through this. So it's basically saying, what would the number of atoms be in order to equal this number if this number were expressed in grams? So let's write that out. It's 24.31, but like I said, I'm converting this to grams. So this is the atomic weight. Switch to grams units. Okay, and now what we need to do is we need to figure out how to convert this to number of atoms, right? But that's okay because we actually have a conversion factor kind of written down for us. It says that the average mass of one atom is 4.03 times 10 to the negative 23rd grams. So let's try to pencil this out. We want to cancel out grams. So I'm going to put grams on the bottom. And we want to cancel out grams of magnesium, right? So I'll just write it out like that. You can include the magnesium if you really want to be thorough. All right, so let's put the grams on the bottom. That way we can ensure that it cancels out. But what we're really looking for is what number of atoms there are. So that should be on top. So put atoms on top. All right, in this case, we know that the average magnesium atom weighs 4.037 times 10 to the negative 23rd grams. So this grams unit needs to be paired with this number. So I'm going to go ahead and plug that number in. So I'll write 4.037 times 10 to the negative 23 grams for every one atom, right? We said that that was the mass for one generic average magnesium atom. All right, so now we can go ahead, we can do our canceling, and we'll be left with the unit of atoms. And when we do this, we get a number that's 6.022 times 10 to the 23rd atoms. So this number shows up regardless of what element you're doing this with, right? We could do this with carbon, we could do it with silicon, we could do it with chlorine. But if you try to find the number of atoms that would be required to make up the atomic mass of a given element or molecule in grams, you'd be left with this number. And this is Avogadro's number. The symbol that you often see for Avogadro's number is N with a subscript A. It's a really common constant that we run into in chemistry. It's also known as the mole. So we use this interchangeably, but a mole of something is 6.022 times 10 to the 23rd. So let's even write that out. So a mole is equal to 6.022 times 10 to the 23rd. And it's important to remember that the abbreviation for mole is MOL. All right, so the way I like to describe this to students is if you go into a bakery and you ask for a dozen donuts, the baker immediately knows that you're talking about 12, right? A dozen always means 12 in a bakery. It's similar with a mole, right? A mole is just a counting tool. And in this case, a mole is always going to be equal to 6.022 times 10 to the 23rd things. It doesn't really matter what you're counting. So I'll even put things in here with quotations. It could be an atom, it could be a molecule, it could be baseballs. It doesn't really matter. A mole is just a counting tool. So it's something that we use a lot in chemistry when we're doing example calculations. It's really important. So let's even write this out in a bit more detail, and I'll show you all the cool unit conversions we can get out of this simple calculation. So for example, we could say 1 mole of magnesium atoms based on this is always going to be 6.022 times 10 to the 23rd magnesium atoms. Right? It's kind of similar to saying 1 dozen equals 12 donuts, right? 1 mole is always equal to 6.022 times 10 to the 23rd. All right. Additionally, we could say, well, 24.31 grams of magnesium is going to be equal to 6.022 times 10 to the 23rd magnesium atoms. Because we just said over here that this many grams eventually works out to be that many atoms. So that makes sense. So we can use this as a conversion too. And then last but not least, we kind of have set ourselves up for a new conversion. If this top part is equal to a mole and this bottom part is equal to a mole, then that means that these two things must be equal, right? So let's go ahead and write this out as our third conversion. So we can say 1 mole of magnesium atoms is equal to 24.31 grams of magnesium. So we can use all of these for conversions. It doesn't really matter which one, or I shouldn't say it doesn't matter. The one you select really depends on what units you're trying to cancel out. So let's go ahead and do a little bit of practice with this. So let's practice again just using magnesium. Okay, so how many grams of magnesium are in 1.27 moles of magnesium? Okay, so let's try to figure out how to set this up. So I always start with what I know, which is 1.27 moles of magnesium. And then I want to use my conversion factor to eventually solve to figure out how many grams there are, right? So let's try to figure out how to set this up. In this case, I need to cancel out moles in order to get to grams. So I'm going to put moles on the bottom right here. And you can tell we want grams out, so I'm going to put grams of magnesium on the top. Okay, so let's look at our conversion factor and find a gram to mole equivalency. So if I look at the first one up here, it says moles of atoms and number of atoms. So that doesn't really help us. We don't have any grams in there, right? So that won't work. So over here we've got grams and number. That doesn't really work. Let's check this one. Oh, I see both moles and grams in this one. So let's go ahead and plug that in. In this case, the grams is paired with 24.31. So I'm going to go ahead and put the 24.31 on top with the grams unit. So 24.31. And that means it would be 1 mole paired with the, or 1 paired with the moles of magnesium. All right, so if we go ahead and we plug this into our calculator, we should get a number that is 30.9 grams. All right, let's do another one. Let's do how many moles are in 105 grams of magnesium. Okay, so again, I'm going to start out with what I know. I have 105 grams of magnesium. I want to cancel out grams of magnesium, so I'm going to put that on the bottom. And we know that our target is going to be moles. So I'll put that on top, because when we do this, we're going to cancel out grams of magnesium and be left with the units of moles of magnesium, which is what we're trying to solve for. Okay, so let's go and look at our conversion factors. So we need a gram to mole relationship, which in this case is going to be that same one down on the bottom. So this time the 24.31 needs to be paired with the grams, but the grams is actually on the bottom. So I'd say 24.31 should go down here. 1 mole goes on top there. Again, if I plug this in, I would get 4.32 moles. And let's just be thorough and leave in the magnesium in here too, so we know which atom we're talking about. All right, let's do one last harder one. And this one, I'm going to say, how many atoms are in 105 grams of magnesium? Well, we could just go from the moles we just solved for in the previous problem to grams, or sorry, to atoms. But let's try to actually do it as a multi-step conversion, because this takes a little bit more practice. So I'd say 105 grams of magnesium. We need to cancel out grams, so I'll put grams of magnesium on the bottom. Really, the only conversion that had grams in it were going to be these two, right? So we have some options. If we look at this one, we could say, well, if we do the bottom one, then we're going to set ourselves up to find moles. We don't want moles, so I would actually go with this one. In this case, we can actually do it all in one step. So we've got 24.31 grams of magnesium are equal to 6.022 times 10 to the 23rd magnesium atoms. So I misspoke earlier saying that we needed to do a multi-step conversion. In this case, we don't. So we can go ahead and cancel out our grams of magnesium here, and we're going to be left with magnesium atoms. So if we go ahead and do this, we keep the colors the same, we're going to be left with a number that is 2.60 times 10 to the 24th magnesium atoms. So make sure you do practice these unit conversions. The number one mistake I see students make is they accidentally flip-flop these numbers. It's important to remember which number goes on which side. It's very easy to mess up unless you practice it a fair amount though. All right, so let's extend this a little bit further. So this same concept can be used with molecules. In my previous video, I showed you how to find molecular weight And we said that we could find molecular weight by adding up the individual atomic weights for the atoms that make up that molecule, right? So let's take an example. So in this example, let's do CO2, right? We've got one carbon atom. Okay, so if we have one carbon atom, we know that that one carbon atom's atomic weight is going to be 12.01, right? And then we've got two oxygen atoms. So I'd say 2 times the atomic weight of oxygen, and the atomic weight of oxygen is 16.00. And when we add this all together, I get 44.01. And let's remember our units in here. We've got our AMU, so this is just going to be our little U symbol. All right, so let's write this out. Same idea. We know that 1 mole is always going to be 6.022 times 10 to the 23rd things. It doesn't really matter what things we're talking about. It could be atoms, it could be molecules, it could be baseballs, it doesn't matter. All right, so let's branch this out. We could say, well, 1 mole of CO2, in this case, would have to be equal to 6.022 times 10 to the 23rd molecules of CO2. Meaning we would have to have that many CO2 molecules to equal 1 mole, right? All right. Additionally, we could say, well, 44.01 grams of CO2 are going to be equal to a mole, because that's the molecular weight that we just determined up above. Oops, that should be CO2. And then last but not least, we could say 1 mole of CO2, let me spread this one out a bit more, is going to be equal to 44.01 grams of CO2. So again, we can use these as conversion factors when doing math with molecules, not just atoms. So it's a little bit strange to think about it that way, but it's really helpful, especially as we get into a topic called stoichiometry later on. All right, let's just do one other abstract mind mapping, and let's consider H2O, right? So the molecule H2O, we know it has 2 hydrogens for every 1 oxygen. So let's branch this out. So 2 molecules of H2O would have to have 4 hydrogens, right? Because if we have 2 molecules and each molecule has 2 hydrogens, 2 times 2 would be 4. So I'd say 4 hydrogens plus 2 oxygen. All right, let's do this as 10. I know this feels kind of silly, but bear with me. If we had 10, then we would have 20 hydrogens plus 10 oxygens. The ratio would still hold true, right? We can do this even further and say, well, what about if we had 6.022 times 10 to the 23rd molecules, meaning an entire mole of water? Then how many hydrogens will we have? Well, we'd have twice as many, right? So if we plug this into our calculator, it'd be 12.044. I guess you don't need a calculator for that. Times 10 to the 23rd hydrogens plus 6.022 times 10 to the 23rd oxygens. All right. Furthermore, we can say, well, we just said 1 mole is equal to 6.022 times 10 to the 23rd. So we could say that 1 mole of water has 2 moles of hydrogen. Right? Because there's twice as many hydrogen atoms in the unit as there are molecules, right? So 2 moles of hydrogen plus 1 mole of oxygen. So this is more just a conceptual linking showing that the ratio of atoms within a molecule holds true regardless of the system of counting, right? We could be counting individual atoms or moles of atoms. It doesn't really matter. All right, the last thing I like to do is just kind of a conceptual mind map for unit conversions. And it's not one I want you to memorize, because memorizing anything just is limiting. I prefer just to use this as a study tool. So we can go from mass to mole, and then we can go from mole to molecules, and then we can go from molecules to mole, and we can go from moles back to mass. So we can start plugging in various unit conversions here to accomplish any of these transformations. So for example, if you want to go from mass to moles, you could divide by the atomic or molecular weight. If you want to go the opposite direction, you just multiply. All right, so we could convert really easily by just looking at the periodic table, and if it's an atom, use the atomic weight that's listed. If it's a molecule, add up all of the atomic weights for that molecule, and we can multiply or divide. So not too bad. And then if we want to go to moles to atoms, that's when we multiply by Avogadro's number. And as you can probably tell, to go the reverse direction, we're just going to divide. All right, like I said, this is something I recommend doing as you study. The most versatile step you have is mole, because you can go either direction, either left or right, in one step. So it's pretty easy. If you're stuck, just get to moles and try to back out that way. But I always recommend kind of laying things out. Make sure your units cancel. Don't just trust to divide. I always like structuring it so that I can see that my numerator is canceling out my denominator unit and that I'm left over with my desired unit. All right, I hope that helps, but let me know if you have any questions.